three things. In this one, we will take this example and try to apply the Gram-Schmidt process in order to get out of this set of three linearly independent vectors that actually, because they're free and are free and they're independent, they span all of R3. But that's besides the point. We could also have three R4 vectors from R4 that would not span all of R4, but they would be linearly independent to each other. But in this case, actually, we have three that are linearly independent and they also span the whole space that they're basically in. But in any case, let's take these three vectors and try to make them perpendicular to each other. The fact that they are linearly independent is nice, that they still span what they need to span. But we could also have another basis for that space. Not these three, but other three that we generate out of these three, where we copy the fact of how much they span, but we won't have the same basis. We will transform it into, again, three vectors, which will nevertheless have an additional property, that they will be perpendicular to each other. And also, Gram-Schmidt process final result is, part of it is also that these three new vectors are unit length. So what I will do at the very end is divide the length of all three of them by their magnitude. All of the three vectors by their magnitude, so I make sure that they're all unit lengths. But that will be beside the point. The main point will be to make them perpendicular to each other. To generate three vectors that span the same like these three, but are perpendicular. So this is a gradual process and an iterative one. We start from one vector, then we work our way towards the next ones along the way. And Gram-Schmidt process works this way because how I start basically is I pick one vector and using projections and so on I continue. So how will I start? Well, I will first call these vectors somehow. So these initial ones that are not perpendicular to each other, which can be proven by the way we do it, is dot product. Dot this one with this one, it's not zero. Dot this one with this one, not zero. And so it ends up proving itself. Well, none of these are perpendicular to each other. No two of these three are perpendicular to each other. But we want the situation that any of these three, when we take two, they're perpendicular. Their dot product is zero. Alright, so we have these three vectors, A, B, C, and they will, well, the arrow is a little redundant. We'll be running it many times and saving the time from using the arrow will be useful. And so, how do I start? Well, I need some basis direction to base everything from. So if I want them all to be perpendicular, in the 3D space, we can imagine it as the three x, y, z axes are by default perpendicular. Actually, although I'm working with R3 here, and I'm going to create a basis that is perpendicular, orthonormal one, it won't necessarily match the unit base vectors of R3, the general basis 1, 0, 0, 0, 1, 0. It won't end up so necessarily. So what we will basically get is some vectors, but it might be rotated a bit. So yes, the three new basis vectors will be perpendicular, but they might be rotated out of the position of the usual x, y, and z axis. And so, how do we do it? Well, I start with one of the three, and then I continue. So how do I work? I say that I need some vectors v1, v2, v3 that are perpendicular to each other. These are not, but these three will be. And these three will span the same like these did. So for the first one, I will say that actually nothing is needed. I will straight out say that v1 will equal to the A. So I will say that this one is v1 already. But the remaining ones cannot be because they are not perpendicular to it. So now I have to continue, and I'm looking for v2 and v3. So I will continue now with v2. v2 needs to be perpendicular to v1. So how do I do it? The process is as follows. If I draw v1 and I draw v2, they're not perpendicular, but I can create a projection that will draw a point from v2, a projection onto v1, and it will draw a point called v2 hat onto v1, such that the tip of v2 minus this point will be perpendicular to v1. So we will generate project b onto v1. That's important. Where v1 is, by the way, the A. So I project this vector onto this one, and that will create this point. And why this point is useful is because I can subtract it from the tip of B, where both of these will start at origin, imaginably. And this connection vector will be a V2, will be my first by work generated V2. So we'll do that. So how to project it? The way to project as well as such is, well, first I really need V2 head. So V2 head. And after I have V2 head, I will only do B minus V2 head, and that will be our actually it's B head, because we're projecting B. So it was a mistake. Be careful about this. It's B head, not because it will lead eventually to V2, but it's B head because it was B projected onto V1. So B head on V1. The B head will be the coordinates of the point that is located on V1 that was projected by B onto V1. So how is that calculated? If we project one vector onto another, the result of which will be that point of projection onto V1, well, how do we do it? Is basically we multiply the vector that is projected onto by some fraction of dot products, and the dot products are as follows. All of this, all these three are just repeated V1, the one that is projected onto, and once here in the numerator in the dot product is the one that we're projecting. That's it. So we need this. This is a scalar multiple of V1. It will be a scalar multiple of V1 eventually. That's the point. Because it has to lie on V1. So it will be a scalar multiple of V1. It won't be all the way till its end. Maybe it will be beyond its end, as we draw it here, but that's not the point. It will be some scalar, some segment, and the direction that is drawn by V1. So B hat, we only need to project B onto V1, and this is the formula of projecting B onto V1. And the analogy goes, if we want to project something on something, it's what is projected onto over what is projected onto dot what is projected onto, and in the numerator is what's projected onto times what is projected. So it's always the thing that is projected is only mentioned once in the formula, while the thing that is projected onto is 4 times there. In one case is the vector that will be scaled, and in 3 cases it's parts of the dot products, where there's 2. Numerator, denominator, and this whole thing will be a scalar, and this whole thing will stay a vector, and this whole scale thing will scale up this, and that is the most important part. So B head is as follows, and now I plug the information in. I know V1 is actually A, so I can straight out use this, and B, I just use the one that is here. And that is 1, 0, 2, and then these dot products. I will just do the dot products as a number and not write them out, all of them, because it would take so much time. And they're also small numbers, so it's possible to do in the head. So it's V1.b, so 1 minus 0 plus 2, so it's 3, over V1, that's 1 plus 4, what's 5. So in all, it's 3 over 5 and 6 over 5 here. You can check for yourself, or in your examples, if you create an example for yourself, or find some other example, you can just practice this very process. So that's it for now. We got B head, and V2 will be something that is perpendicular to V1, and something that is perpendicular to V1 is this. So this thing will be V2, the B minus B head. This will be perpendicular to V1, and therefore it will equal to V2, because it's perpendicular to V1. And we want this new V2 that we generated to be perpendicular. That's how we made it. So what will it be? B minus B head. So use this B head and subtract it from B. 1 minus 1, 1, minus 3/5, 0, 6 over 5. And it is 2 over 5 minus 1 minus 1 over 5. So that's V2. So we got V2, I will write it here, out of the range so it doesn't take space. Minus 1 minus 1 over 5. So we got it. And now we're getting very close, and the Gram-Schmidt method, and by the way, V2, okay, it has this direction, but I can scale it up. The direction won't change. I can multiply all entries by the same. So I will multiply all entries by 5. That's exactly what I did now. So 2 minus 5, 1, minus 1. So that's V2. And V3 will be similar. We'll precisely use U3 now. And we will use the vector so far generated also. We only generated V2. V1 was basically just query out of A directly. But V2 we actually had to work for a bit. And so V3, what it will be is, oh, actually that's not U3. Sometimes it's called U3, I call it C here. So for V3, my basis will be again projecting. How will I do it? Well, I need to project. So let's say that now I will do this, how will I call it? C hat, because before I had B hat, right? Now I'll have C hat, and it will be the projection of V1 and basically it will be the projection of V1 and V2 onto C. So the things we have so far to project them onto C to make sure that V1 and V2 will therefore be projected onto C, and then we can again do the formula C minus C hat, because that will generate a third perpendicular vector. So C hat for now, just like we did if in case there's confusion, we can skip a few minutes back where we did B hat. And this is just the same idea brought to the next step. We always iterate. What we have so far, we used further. So C hat, what will it be? It will be precisely a combination of what we have so far, a linear combination, actually, scaled up of the two vectors we had so far. Before, we only had V1 concerned, but now we also got V2. And the third one has to be in relation to the previous two. If we had a fifth one, it would be in relation to all the previous four. So, how is it going to be scaled up? No, the only thing you have to do is scale it up by the projections. The rest of the projection formula, dot products. So, just like we had before, we are all now projecting C on everything. So, it's C dot V1 and V1, V1, because here was V1. Then V2, always what is out there is also many times inside here. And then C again, projected on V2 also. So this one is project C on V1, this is project C on V2. But now what we have to do is we have to subtract C minus C hat. 1, 1, 1, 1, minus this. 10 over 30, 20 over 30, 40 over 30. So what is this? Well, that's 20 over 30, that is 10 over 30, and this is minus 10 over 30. So we got here something that is our V3 direction. So our V3 will be this or any rescaling of it. I will rescale it to 2, 1, minus 2. Minus 1. Alright, so we also got the V3. We now have all three vectors, perpendicular vectors generated. And now we can check that they are perpendicular. So, how do we do that? Just put them in dot product with each other. So, make sure that they're in dot product with each other, and then they will make a 0. So, here they are, these three. So, let's check any combination of two of them. So 2, 1, minus 2. I'm checking V1 and V3 together, the most distant ones. So it's 2 plus 0 minus 2, so it's 0, right? Then I'm just gonna write it V3 dot V2 and do it like this. 4 minus 5 plus 1, yes, that's 0 also, so that's fine. And the last one we want to check is V1 dot V2. Also 2 minus 0 plus minus 2, so is 0. Yes, so they're all perpendicular to each other, and this process was successful and correct. And now, also the very final of Gram-Schmidt processes, we want to make them unit length. Now we don't have unit length, so let's make them unit length. Let's say that the very result won't be V1, V2, V3, but it will be W1, W2, W3. These three vectors will be our very big main result. So to do it, I only divide the whole vector, each entry by the whole vector's magnitude. That's it. Just making it a unit vector. So this is going to be 1 over the square root of 5, 1, 0, 2. For V2, it's going to be 1 over the square root of 30. times this, times what it is, 2 minus 5 minus 1. And for the third one, it's going to be 1 over the magnitude again, 4, 1, 1, so over the square root of 6 times 2, 1 minus 1. So we have this, we have 3 vectors that are perpendicular, have the same span like our initial ones, and our unit length.